Okay, so let's get started. So last time we talked about special uh, uh, bialgebra structure associated to a Poisson Lie group structure on a Lie group. So just a reminder, the Poisson structure is just a Poisson bracket, which means a Lie bracket on the space of functions, which satisfies the Leibniz relation. Okay, so maybe I should just show the definition of a Poisson bracket from last time, from 2 lectures ago. So a Poisson bracket on an open domain or on a manifold is just a bracket, a Lie bracket together with the third property, which is a Leibniz property. And in principle, a Poisson bracket is some expression which depends on the partials, like first order partials of the functions f and g. So in the examples that I gave, for instance, you saw that the Poisson bracket is this kind of a linear combination of the partials, the first order partials of f and g. In general, we could have some expression of the form sigma wij partial if partial jg, where partial I means ddxi, partial j means ddxj. Okay, so any Poisson bracket will look like this for some function wij, some like rather some family of functions wij, depending on the indices I and j. Okay, so this is not so difficult to see. And then we defined a certain Poisson structure on the dual of a Lie algebra, but after that we talked about Lie groups which have a Poisson structure that is compatible with the multiplication map. In other words, the Poisson structure on G naturally induces a Poisson structure on G cross G, and a Lie group equipped as a manifold with a Poisson structure is called a Poisson Lie group if the map mu is a Poisson map, which means it is compatible with the Poisson structures on G cross G and G. Okay. And one thing we learned from last time was that starting from a Poisson structure on capital G, which means starting from Poisson Lie group, we can obtain a Lie algebra structure on the dual of the Lie algebra. So if you start from capital G, this fracture G is a Lie algebra. This is like one of the earliest things we learned in this course. But now, if G is also equipped with a Poisson structure to make it a Poisson Lie group, then it happens that G star is also a Lie algebra. It has a bracket. That Lie bracket was defined according to this formula. So you take the Poisson bracket. Okay, if I can get it to right here, I'll do this for you. Okay, so basically, I need to tell you what is the commutator, what is the Lie bracket of two elements in dual of the Lie algebra. So I take functions whose derivatives at the identity are these vectors, and then the Poisson bracket only depends on these partials. But it happens that in the case of a Poisson Lie group, the derivative of the Poisson bracket, which is a function on capital G again, also only depends on Kc1 and Kc2. That's basically because when you write this formula and use the fact that the Poisson structure is compatible with the multiplication map, you learn that the Poisson structure F1, F2 can be expressed as sigma partial W, partial K, Wij, partial IF, partial JG. So you will not have order 2 partials in F and G. That's because one can show that Wij at the identity are all zeros. Okay? But I'm not going to explain those calculations now. I just want to say that, in fact, this derivative also only depends on the partials of only on the first order partials of F1 and F2, which means on dF1 and dF2. Okay? And therefore, since we had a Poisson bracket, which was a Lie algebra structure, we automatically get a Lie algebra structure on G star. Okay? And then one can see that this Lie algebra structure also talks to the Lie algebra structure on G via the following relation. So delta of xy is x delta y plus delta xy. Okay, kind of like a derivation. It's close to derivation, not exactly derivation, but looks like a derivation kind of formula. All right. One thing I wanted to mention was, so last time, I was explaining this argument that the structure that I defined on G star on the dual of the Lie algebra is indeed the Poisson bracket. And we got stuck in the argument of the Jacobi identity. So I added the details there. Remember, then when we wrote out everything, we got to such expressions. Well, we got to these expressions for the like triple brackets. And then we saw some cancellation of terms. So all that was left was some expression like this. All right. So when you write the Jacobi for the Poisson bracket on G star, you see the right-hand side. And now you have to verify that the right-hand side is 0. So I added the details why this is so. So the point first is that, as I mentioned last time, that the WKLs are just linear maps, okay, from the formula we had. In this special case, the WKLs were linear. They were these maps. They depended linearly on alpha. Okay, this was just alpha of something. And if you write that something, you see that is actually better than the formula we had before. So I've added this here. So Wij alpha is alpha of this linear combination, sigma over u of Cij upper u x sub u. But this is exactly the expression of the bracket. In other words, Wij alpha is just alpha of xi xj. Okay? That's a simpler way to see this. And then when I write this expression, Wij cklj, oops, I shouldn't have raised this. When I write this and I sum over j, so now, well, I can replace each Wij alpha with what I just got, which is like alpha of this xi xj. But now I have a summation over cklj. So I just bring this inside. And then I note that the thing inside, if I move the summation inside now, this is just the expression of xk like xi xk xl, because so this is the expression of xkl xkxl, I'm sorry. So xkxl equals sigma over j ckl upper j xj. That's just by the definition of the structural constant Cijka. Okay. So this means that, in fact, Wij alpha ckl alpha, this one term is really this alpha of one term in the Jacobi identity. And the same thing happens for the others. So you get the Jacobi identity terms for the Lie algebra G, and when you add these guys, the sum of those terms will be 0. It will be alpha of something plus something plus something, and that thing is just the sum of the 3 terms of the Jacobi identity for the Lie algebra G, and that vanishes. Okay, so this is just to clarify the last bit of the argument from last time. All right, so now back to what we were discussing again. So let me scroll up again. So we learned that this Poisson structure on capital G results in this Lie algebra structure on the dual of the Lie algebra on G star, and it also talks to the Lie algebra structure of G as such by this condition, which is sometimes called the co-cycle condition. Okay. And we were doing some example, and I left some of the details of the example to you to do, and I will put this in the last assignment, which I'll post in the next couple of days. All right. So what we would like to do now is we would like to see how we can actually get some Poisson structures on a given Lie algebra G. In other words, how can we construct? Okay, I shouldn't call it the Poisson structure. I should say how we can actually equip a Lie algebra G with a bialgebra structure so that it potentially corresponds to some Poisson Lie group. Okay, or rather Poisson structure on the corresponding Lie group. Okay, so that's the thing we want to explore today. So let me just show these lines, which will help me draw things more nicely. All right. Any questions so far about what we discussed? I'm happy to explain whatever we discussed so far again. Anything we discussed? Okay, because like things are piling up now. It's becoming more and more sophisticated. All right. Okay. All right. So here's the question. So given a Lie algebra G how can we construct delta going from G to G cross G to make the pair G delta a Lie bialgebra? So here is a simple way that one can proceed and see if it will succeed. Okay, some idea, and the idea is the following. So this is maybe okay. So maybe some okay maybe idea. So we try delta x equals, or maybe I just call it delta sub Rx. I'll specify what R is. This is x dot R for R, some element of G tensor G, where this dot is just the action that I described last time. So more specifically, if R is this 2 tensor, which can be written always as some linear combination of these pure tensors, some finite sum like this, where the UIs and the VIs are all in G, then we want to set, then, or rather we have, I mean, by the above definition, delta Rx is, well, how does an element of the Lie algebra X act? Maybe I should specify that little x is also in G. How does it act on a 2 tensor? This I described last time. Act on the first, leave the second, act on the second, leave the first, and then like add up the results, okay? So I should write x ui, I want to make sure that my sound, okay, x ui tensor vi plus ui XVI. And of course, I have to make a summation over all i's. Okay? Now, why do we do this? Because there is this complicated condition, I mean, at least complicated looking condition, this co-cycle condition. All right? But somehow magically, when we define delta as such, as delta sub R, this co-cycle condition is automatically satisfied. All right? So let's check. Okay, so here's the lemma, which is that delta R satisfies the co-cycle condition, which is delta R xy equals x delta ry plus delta rx. Okay, I should have written them in the other order, but it doesn't really matter. Okay, so we want to check that this is actually satisfied. Well, this is just a calculation again, but it's maybe worth doing this to become more familiar with these 2 tensor calculations. Okay, so what is delta R? So here's the proof. So what is delta R of xy? Well, by the formula for the action, I have to just replace this x in this formula all over the place by xy, okay? So I end up with the summation over I of xy ui vi plus ui xy vi. Okay? And now I have to write the other terms and then add them and see if we get the same thing. So I have delta R x y. Let's do this calculation. So first, I should do delta Rx and then take the commutator with y the way I defined this commutator, okay? So what is delta Rx? Well, I know that this is just x ui vi, and I should take now the commutator with y, and then the other term would be ui xvi, and then I should take the commutator with y again. Okay, so now each of these commutators actually produces two terms. I have to take the commutator with the first and tensor with the second, plus first tensor commutator with the second. Okay, so for the first term I get, and this is a summation over all, like always over I, so I get x ui y tensor vi plus. Then I have to keep the first term, which is xui, and I should write now viv, viy. Okay? So I'll just keep writing the two terms. They're all under the same summation over the same index I. But I'll just, I will not write another sum. So then the next term, I have xi y xvi. I'm sorry, this is ui, not xi. I called it xi. It's the ui. And then I have ui xvi y. All right, not that bad, just 4 terms. Okay. And the other one, what about the other one? We have x delta ry. So first I write first I write this bracket x, and now what is delta ry? So first I have this y ui vi, and then I have this ui y vi. And again, in the end, I end up with 4 terms. Each of the two things under the summation, under like in the bracket, should result into 2 things. So first I have this x y ui tensor vi plus y ui xvi. Then I have 2 other terms under the same summation, x ui tensor yvi plus ui x y vi. Are you following this calculation? Are you following this calculation? Is it good? All right. So now let's look at the two and see what happens when we add these guys. So, and also compare to the previous one. So we needed, the previous one, we needed this x y ui and x y vi in the components. Basically, we have to like a kind of collect the coefficients of tensor vi in everything. Okay, so let's look at the coefficient of tensor vi. So here, tensor vi, where do we have tensor vi? Here we have 1, and here we have 1. Okay, so what you have is just some bracket involving the same 3 things: x, ui, and y. You see, this is x, ui, and y, x, ui, and y, x, ui, and y. And in fact, this is another way of writing the Jacobi identity. But the Jacobi identity, you can write the sum of 3 things equal to 0, or one of them equal to the sum of the other 2. Okay, so that takes care of equality of whatever tensor vi. But there are other terms on the right-hand side. So the other terms would be those which are not tensor vi. For example, we have this term, we have this, and we have this we have to worry about, and we also have this and this. But these guys again automatically cancel out, because here I have, say, xui vi y, and I have now xui y vi. VI, Y, and Y, VI are of different sign. So they cancel each other. Okay? And same here. This guy and this guy. So I have UIY x VI. Here I have YUI x VI. They cancel because this and this are opposite sign. Okay? So the conclusion is that nice cancellations occur. And the cocycle relation holds. So some of you took other courses with me, and this observation should remind you of something. Maybe more specifically, some of you took algebraic topology with me, and now this observation that delta R satisfies the cocycle relation should resemble something. Have you seen something? I mean, do you remember anything from that course? So back then, when we talked about homology, so we had the notion of this operator D, this boundary operator. And the square of D was 0. In other words, there were some elements in those homology groups which are automatically a cycle. Their boundaries were 0. Here I use the word cocycle to remind you of the word cycle there. Okay, so the point is that in some sense, well, maybe more in like kind of a homological language, the delta R's defined as such are somehow coboundaries. So they are designed to have their delta V0. In other words, in some homology context, these are the sort of coboundaries, so that when you apply this D operator, which would be this, whatever this calculation means, then you should get 0. In other words, the calculation means like this cocycle difference, the difference of the two sides on the cocycle. All right. In other words, if this delta R results in some Lie bialgebra structure, then that Lie bialgebra is sometimes called a coboundary Lie bialgebra. Okay, because it came from some delta R, which was the coboundary. So automatically was a cocycle. All right. Okay, so now what we know is that delta R like satisfies this peculiar condition, but there are now easier conditions that it should satisfy, right? So in fact, this delta should dualize to a Lie algebra map, right? So we sort of took care of the difficult condition, or rather the condition that was kind of mysterious condition. Maybe I should call it a mysterious condition. But we still don't know if a delta satisfies the mysterious condition like a delta R. We don't know for which delta R we actually do get a Lie bialgebra structure. But remember that delta star is supposed to be a Lie bracket, so it has a skew symmetry, and this translates into skew symmetry of delta, because delta is the dual of delta star. And the Jacobi identity for the delta star should also translate into some relation on delta. Okay? When you write out those relations, you get the following, which I said as the form of the proposition. So here's the proposition. So delta R defined above makes G a bialgebra if and only if R satisfies the following. So R should satisfy two conditions which reflect the skew symmetry and the Jacobi identity of delta star. Okay? The calculations are not really difficult. I mean, they're just tedious, but I'll just state the final statement, which is the most important thing. So the first is what sort of states for skew symmetry, and that is that R12 plus R21 is G invariant. So there are two terms here that I should define. So what is the first thing? The first thing is what is R21 here? So R21, so if R is sigma UI tensor VI, as an element of G tensor G, then what do I want? I mean, now you should tell me. Sometimes when you look at some unknown notation, you can guess what it should be. So what should R21 and R212 be to reflect the skew symmetry? How should I interpret? What do I want to say by this? Say that again, please. Well, we don't have any x1 here, so we have ui's and vi's. So if I wanted the tensor to be skew symmetric, I wanted something like the sum of the ui tensor vi's plus vi tensor ui's to be 0. Okay. So this R21 should actually mean this, meaning just switching the indices. Switch the indices 2 and 1. Okay. So this R12 is just sigma ui vi, which is the same as R. And this should be just sigma vi ui. In other words, switch components. In other words, this indexing says the second component becomes the first component and the first component becomes the second component. It tells you the order of the components now, how to reorder. And this is pretty standard notation in half algebra theory and quantum groups. So this is fairly common. Okay. Any questions about this notation? So I just explained to you what R21 means and R12 means. Now I have to tell you what invariance means. So R12 plus R21 is another tensor in G tensor G. Okay. So now we say S in G tensor G is G invariant if any element acts on this tensor, it results in 0. In other words, X S is 0 for all S in G. In other words, if I write this as sigma S, if I write this as sigma AI tensor BI, which I can always do, so this means, well, I have to apply X to the first component and tensor with the second component, and then write the first component and tensor with the second component applied with like a X applied, with X applied. And I would like this to be 0 for all X. Okay? Any questions before I just scroll up so I can show you the condition again? Everybody happy so far? So the first condition, so this corresponds to the skew symmetry of delta star. This is the first condition that R should satisfy. And the second condition that corresponds to the Jacobi looks a little bit complicated, but well, more complicated than this one. Not too bad, but let me just write it out. So I have R12, R13 plus R12, R23 plus R23, R13, R23. Should be is G invariant. Now here I have to define two things. First, I have to say what is R13, and second, I have to tell you how I take the commutator of these guys. Okay? So let me explain this. Any questions about, like, so I just wanted you to stare at this and for a moment, and then I'll just explain all of this, what this notation means. Okay, so what are these guys? So again, remember, R was some tensor of the form AI tensor BI. Now, this time, because we have this index 3 involved, R12 means something slightly different. So R12 means sigma AI BI tensor 1. So this is now a tensor in the threefold tensor product. And R13, it means you put the components of R in position 1 and position 3, and position 2, you just put a 1. So you have AI tensor 1, tensor BI. Okay, so here we have to be a little bit careful. Okay, so now, okay, it is not, okay, so it's a little bit funny. So it's, we don't have a 1 in the Lie algebra, but we think about that component as a 1. And when we take the commutators, that 1 disappears. So we have something which makes sense. So let me show you how it works. So the first thing is like I have to do R12, R13, right? So what is R12, R13? So, well, I have the summation sigma AI tensor BI tensor 1, and I have another summation over J, sigma AJ tensor 1 tensor BJ. Okay, so now when you want to do the commutators, remember these tensors are all bilinear. So now the first component in all of these are the same. Okay, that's not quite right. Okay, they're not the same, but what happens, okay. So what happens is that, okay, so you should interpret these two as commuting tensors because one commutes with everything. So what you should write, so this is something like AI. So this is formally, maybe I should write formally. We have the AI tensor BI tensor 1 multiplied by, or maybe just write one commutator, AJ1 BJ. It is like AI BI 1 AJ1 BJ minus AJ1 BJ AI BI1. Okay, so I kind of assume that I'm in some associative algebra. Okay, now if you know what a universal enveloping algebra is, you could think about all of these expressions inside the enveloping algebra of G. Yeah. That's exactly what I'm trying to explain. So I put this in quotation marks because 1 doesn't make sense in G. But what I said is imagine that, in fact, G was a Lie algebra inside some associative algebra. For example, like GLN, which is both a Lie algebra and an associative algebra. Imagine that, in fact, I had an associative algebra. So it's independent of the chosen. That's right. So let me finish this and you'll see that that's happening. Okay. So when I write this, so now I'm doing the sort of a usual commutator, like in associative algebras, right? The usual Lie bracket in an associative algebra. But when I multiply these, so in the first component, so what is the first guy? The first guy is AI, AJ, and then I should multiply these. I get BI, BJ, right? So for the first term, I get AI, AJ, tensor BI times 1, which is BI, tensor 1 times BJ, which is BJ. And for the second one, I again have AJAI now. Tensor 1 times BI, which is BI. Tensor BJ, tensor 1, BJ times 1, which is BJ. So now I see that I have common components. And these tensors are linear in every factor. So basically, I now have to take the difference of the first component. So in the end, I end up with the AI AJ minus AJ AI tensor BI tensor BJ which now in the form of, in the like using the Lie bracket, I can write as AI, AJ, BI, BJ. The summation happening over all I. Okay, I don't have summation yet, but in the end I will have a summation, okay? So I explained to you what the bracket of two such formal things means. This has a rigorous interpretation. You can imagine that these expressions are in the enveloping algebra of G, but if you don't know what the enveloping algebra is, you could just assume this is like a formal calculation, which in the end results in something well defined. Okay, so now what is the conclusion? So in conclusion, R12, R13 should be thought of as defined by the following formula. Sigma AIAJ BIBJ. And this is well defined because the only thing I used was a bracket of the Lie algebra. So this is again some 3 tensor in G tensor G tensor G. Okay. And now there's maybe one more, which is a little bit different. So that is when I do, maybe I just write similarly. If I do R12, R23. So I should think about this as the sort of the sum of these formal brackets. So I can put them in quotation marks. So you have AI, BI, 1. This is for the R12, which should have 3 components. The third component is 1. And the R23, it's like 1 tensor AJ tensor BJ. Okay? And now when I do the commutator, well, I end up with AI tensor BJ, BI, AJ tensor BJ minus, again, AI. So the main point is that the first component in such a commutator remains AI. And the last component is BJ. But over here, I will have the difference of the two things. BI AJ minus AJ BI. So I have basically BI AJ as a commutator. Which is a well-defined tensor in G tensor G. Okay? And now the Jacobi identity really is tantamount to condition 2. That this 3 tensor, when you add these 3 guys, this 3 tensor is G invariant. This guarantees delta star is satisfied the Jacobi identity. So if I want to write out all these conditions, it will, fill up pages. But, this is some calculation that is doable, just like all the other calculations that we managed to do after getting stuck sometimes. All right. So any questions so far about these calculations or about this assertion? So the main point is like when the coboundary delta R gives you a bialgebra. So it has to satisfy these 2 conditions. The first condition is not that bad. The second condition is like more sophisticated and more important. And this condition is called the classical Yang-Baxter equation. Usually abbreviated as such. Classical Yang-Baxter. Maybe I just write it once. Classical. Okay. Any questions so far? Okay, we still have time. All right, good. Should we proceed? Any questions? So now I would like to provide another perspective to this Yang-Baxter equation, classical Yang-Baxter equation, from a completely different point of view. Okay. And that's the perspective from representations of braid groups. So what is a braid group? Does anybody know what the braid group is here? Yeah. That's an algebraic description. Is there a more sort of a concrete description? That's right. So the braid group is a group that basically describes tangles formed by n strands connecting n, say, pins on top and n pins at the bottom. So what do I mean by such a tangle? I mean, for example, if you have a tangle with 3 strands, it will be a way of connecting these points by strands, n strands from n points from the top to n points from the bottom. Now, the strands can go up and down each other. They can sort of get around each other. So, I mean, another example would be, say I have, again, 3, but this time I could have maybe these guys sort of twisting around like this. And maybe this one goes underneath here. And this goes here. This comes here. Okay. So this is another example of a tangle. Okay. So the braid group is meant to be an algebraic way of understanding these tangles, trying to say like how different they are. Okay. In other words, it's a group structure on tangles, or rather a group whose elements are these tangles. Okay. So maybe this, so therefore maybe I should say, so the braid group Bn its elements are tangles formed by n strands connecting endpoints of on the top to endpoints at the bottom. Okay, and these elements are meant to, like, say the topological difference of tangles. In other words, if I draw this one, maybe I just draw it underneath here. That's a better picture. Okay, if I draw this, or I draw this, they are actually unequal elements of this group. Okay, I haven't told you what the composition is, but I'll tell you momentarily. But I just want to emphasize that we want to say the difference, like we want to identify the difference between these two guys. If you think about, like, if we label these with numbers 1, 2, 3, 1, 2, 3, and say 1, 2, 3, and 1, 2, 3, from any tangle, we can construct a permutation. So this would correspond to the permutation that maps 1 to 2, 2 to 1, and fixes 3. So this is just the transposition 1, 2. And same here, this is also the transposition 1, 2. So if you think about these, if you just forget about how the strands go up and down each other, we get a permutation, but those permutations do not distinguish all the tangles. There's infinitely many different, topologically different tangles, whereas there's only like n factorial permutations. Okay, is it clear what I'm saying? Is it clear why these two guys are different? Because there's no way to move the strands around to get this on top. Okay. I mean, yeah, you're not supposed to move the strand above the sort of point that's attached. Yeah. Pardon? Yeah, the group operation. So what is the group operation? The group operation is simply by composition of, or rather concatenation of the tangles. So given, and maybe I should call these tangles braids. So given 2 braids, A and B their composition is the braid Now, you can put A on top and B at the bottom, or you could do it the other way around. It doesn't really make a difference. Maybe it's more conventional to do it this way. So what this means is, for instance, if I take, say, this tangle, so if A, say A is, oops, did I just kill my OneNote or something? Ah, here it is. Okay, so example. So if A is this one, and B, say, is this one. So then the product AB is the tangle that's formed by putting B on top of A. Let me just write here AB, okay. So it will be this, and then I have this, and then I will have this. Okay. Ah, I wrote it in the wrong position, sorry. Okay. Yeah. Okay. But actually, if B, so if but or maybe I should say, but if C is this guy, so then what is AC? So I should put A here. So A is like this. And then I should put C on top. Okay. And now this happens to be, I can just move the strands like the top one on top of the other one. I can just slide it over to actually get 3 parallel strands. And this is the identity element. Not surprisingly, totally untangled. Okay. What this means is that, in fact, C is the inverse of A. Okay. So now it's not so difficult to see that every element has an inverse. Just you have to reflect that tangle and put it on top. Then any sort of way the braids are tangled can be untied. All right. And like associativity of composition is clear just because we're just drawing diagrams on top of each other. That's just like trivial matter. So we do get a group structure. All right. Now, this group can be described by some generators and relations nicely. So what are the generators? We basically, it's not so difficult to see that braids with only one, like with only 2 pairs of successive strands going on top of the other, one going on top of the other, are fundamental, which means any other braid can be described as composition of such braids. Okay, so here is the remark. The braid group Bn has n-1 generators. So what are these generators? So you have n strands, but in the ith position, so this is I-1, and in the ith position, You can decide maybe I goes on top of I plus 1 for all I. Okay, so this is like a basic braid, and any braid can be described as composition of several of such braids. Okay, you just have to sort of scan it from bottom to top and see at each time you hit a crossing of the two strands, you know it's one of these simple braids. Okay, all is good. You just have to make sure that crossings are not are different heights, but there's only finitely many crossings, so, or you could assume there's finitely many crossings. Okay, all is good so far. Everybody following? All right. Now, what are the relations between these generators? One relation I already described. Well, if I call this SI, well, I have to tell you what SI inverse is, but SI inverse is just what I showed you. So SI inverse, it's just when the two strands go in the other direction on top of each other. So I have this. Right? And obviously SI inverse equals SI inverse SI equals the identity. There's a second relation between the SIs, and then that's it. That's all the relation. What is the second relation? Any question about the braids and the relation so far? Is everything clear? Do you have any questions? Do you want me to show a particular part of the slides? Yeah?
Can you find an example that has more than one intersection? And why the inverse of a braid has more than one intersection?
With more than one intersection? Well, we already did one. This is an example with more than one intersection. Well, the inverse of this, you first have to, so I mean, you have to invert this one. So I mean, okay, I mean, how can I draw this? So maybe you could first, oops. Maybe, so I draw with a different color than I erase. So first you could do this. And then you have to undo the other one. So you have to, so this one should go underneath. The other one should go on top. I think this will undo everything. First, I mean, you see this part can be undone. And then, I mean, this is connected to here. And then the other strand moves on top of the other one. Is it clear? You see what's going on? Yeah. You just have to reflect in principle. See, this is like a reflection. Yeah. Which is not surprising because as I said, any element of this group is a product of these SIs or the inverses, right? So now if you have some sequence SI1 plus minus 1 up to SIK plus minus 1, what is the inverse of the sequence? It's SIK minus plus 1, SI1 minus plus 1. Okay? That should be the inverse in the group. And it is topologically as well. Okay, is everything clear then? Any questions? I'm happy to answer any questions because this is like a very basic and concrete. And right. So before we get to the classical Yang-Baxter equation, we at least need to understand what's going on. Okay. Now, okay, what is this? What are the other relations? So the other relations. So if I take two of the generators, what happens to the product of two generators? Well, first, if the two strands, or rather the two intersections of the strands are far from each other, then you can just push them up and down and there will be no difference in the braid. In other words, if I have, so if I minus j is bigger than 1, then SI equals SI. So the generators commute. So why is that so? Well, I mean, I'll show this by some picture. So if, for example, I do this product, this is S1, S3. And I could do S3, S1. S3, S1 would be like this. Okay, maybe this is S3, S1 actually, because we're counting from bottom to top, and this is S1, S3. Okay, so these two braids are really the same because I could just push this intersection point up to come it to this height and push this one down without any other thing sort of being distorted. Like, I mean, the other strands do not get tangled or anything. Okay. So this is one relation, but I could not do this if I minus j was 1. If I have two successive intersections, then there will be a little bit of a problem. So let's just draw a picture. But over there, there is one more relation. So what happens if I have j equals I plus 1? So I have the following picture. Oh, I have to change my color. Okay. So if I call this I and I plus 1 and I plus 2 and all the other strands are just untied totally, then this is the product SI, SI plus 1, SI. Remember, we look from bottom to top, and that's what it is, okay? I mean, it doesn't matter really, but anyway. So now, so here, one thing I can do is I can now push this strand past this intersection point. Okay? I can just move it the other way. And when I do this, I get the following picture. The picture where, so remember, this strand goes before this, so it intersects the one that goes through I to I plus 2 here. So I will end up with the following. Maybe I should just move it up a little bit. Okay, sorry. Okay. So this is the same as this guy. Okay, it just moved past that intersection, and that intersection, of course, was pushed to the left a little bit, so we see the picture better. But topologically, they're really the same. And what you see now, if you count from bottom to top, you now see SI plus 1, then SI, then SI plus 1. And these two things are the same, okay? Because I only got them from each other by sliding the strands without passing through the pins or anything, like crossing the strands, okay? So I have to have this relation. Okay, all is good so far? Okay, so I got these relations, and I got these relations, which are sometimes called braid relations. I mean, the most interesting braid relation. Okay. And in fact, the braid group is described by these relations. In other words, it is the group generated by S1 up to Sn minus 1 modulo these relations. The relation with SISJ commuting for I minus j bigger than 1, and this third relation. Do you have an explanation for this? Why should it be so? Why should it be all the relations on the braids? Do you know why? The reason is a certain result in topology about Yang-Baxter move. So in topology, one can show that if you have two knots that are topologically the same, then you can get to one from the other by a sequence of moves that are called Reidemeister moves. And these moves are something like, so you have something like this, which you want to replace by this, or you have there's a second move which I kind of forget. Maybe it's the same as the second movement, I forget. And there's a third one which is this operation I did, passing through a tangle. So there's 3 Reidemeister moves, and there are really some very basic movements that everybody believes if you do this to a knot, it will not change the knot topologically. Okay. And well, basically these relations that we give here describe all the Reidemeister moves. You can see that whatever Reidemeister move you could do, you could describe in terms of these relations. Therefore, these should be the only relations on the braid group that distinguish all the braids. Yeah. Something like this. Let me draw it. I mean, so something like this to become parallel. Is that it?
Yeah.
Okay, maybe that's it. Okay, so this is also okay. So then this is the same as the first relation, si minus 1 equals identity. Okay, so that's really captured there. And the third one is so here we don't really need to okay, do we need to think about this relation or not? Well, yeah, I mean, but this relation is not described by involvement of more than one generator. In other words, every braid can be described in a way that you don't have self-crossing of the strands. You could say that all the strands are always moving downwards, so you don't have something coming up and going down. That's a restatement of the fact that all the braids can be described as products of these generators. So in some sense, that first, possibly the first Reidemeister move, which I described here, you can sort of wipe it under the rug. So therefore, the relations that we impose are the same as the Reidemeister moves, the 3 fundamental Reidemeister moves. Okay. All is good so far? Okay, so now we have this braid group. All right. So now you can ask, you have a group, maybe you want to give a realization of that as a matrix group. Maybe in other words, maybe you want to understand, maybe you want to look at homomorphisms from this complicated group into a group of matrices. We've been doing this a lot in this course, right? All right. So this is what we can call a matrix representation of the braid group. So a natural way to do this is that you take a vector space and then you think about this generator Si as swapping 2 factors in like several tensor products of this vector space by itself. So more precisely, we can consider, so take any vector space. I mean, any non-trivial vector space. And well, we want to get a realization of the braid group inside GLW. So we want a homomorphism from Bn into the group of invertible linear transformations on W. Okay, so a sort of a simple-minded way to do this would be to take some linear transformation. It's on linear map. From V tensor V to itself. And now define phi of Si. So this is a capital S. It shouldn't be confused with the lower Si. So this is going to be the map from W to W, which keeps all the tensor factors the same, except for the I and I plus 1. So I have, maybe I should write I minus 1 components are not going to change. And then component I and I plus 1 are going to be affected by this S. And then n minus I components after that, nothing is going to change again. N minus I, yeah. N minus I minus 1, sorry. This is like this involves components I and I plus 1. So you have n minus I minus 1 components after this. Okay? So now if I want this to be a group homomorphism, some relations should be satisfied, right? So first, what about the relation? Well, I mean, we can say that like S inverse, SI inverse goes to S inverse. So maybe I should take some invertible linear map here. And then I know where SI inverse goes to. It goes to like the tensor with like S replaced by S inverse. But now I have to worry about those relations. So if I have the relation SI equals SJSI for I minus j bigger than 1, well, this relation will be okay because when I write this phi SI Sj, this is phi SI phi Sj, and I have some tensor for the first one in some position I plus 1, and in the other one some position jj plus 1, and these two s's are in different components. So in the end, I end up with like some 1s, then I have s, then I have 1s, and then I have s, and so on, which is the same as like phi of Sj, phi of Si. Just because the s's are in different positions, they will not interfere with each other. Just the way that we saw that those two strands, when the sort of crossings are far from each other, they do not interfere. Like it's like S is acting on here, the other S is acting on here, so nothing is really being affected. All right. So this is phi Sj, phi Sj, Si. So this is okay. But the other relation is not quite okay. So we have to worry about like this. In other words, the other relation imposes some condition on S. So the relation Si plus 1 Si equals Si plus 1 Si plus 1 implies that if I think about these S's as transformations on triple tensor product of V, then there should be a relation. And that is the following relation. S tensor 1 tensor S tensor 1 equals 1 tensor S tensor 1 1 tensor S. So you have to be a little bit careful about the interpretation here. So here S tensor 1, it's a map from V tensor V tensor V to V tensor V tensor V tensor V. And what it does, if we take some U V W, it maps it to S of U tensor V tensor W. And then this 1 tensor S, it maps this U tensor V tensor W to U tensor S of V tensor W. So you see that they interfere. The second component is involved in the two calculations. So this relation is not automatic. So we need to choose some S which satisfies. Now here is the simplest example of S that does it. So what about the simple, like the following example? I mean, maybe I should say the trivial S. What do you propose? The identity, but then we will get a trivial group homomorphism. Let's try to get a non-trivial group homomorphism. If you set S equals identity, then all the SIs go to identity. You just got the trivial map. Okay, that's not interesting. Let's try to get at least something non-trivial by something like by an S which is almost trivial. If I can get, pardon? That's right. So swapping them. So let me see if I crashed everything here or not. Okay, so I have like Y tensor X. Then you can see that this relation holds. Okay, and the reason it holds is that in fact it's a relation about permutations. If you remember the presentation of the permutation group using the transpositions, you see that it also has these n-1 generators which satisfy this relation and this relation, SI-SJ equals SJ-SI, and the third relation, which is SI squared, is 1. So that's a presentation. That's a description of the symmetric group on n letters by generators on relation. If you had this extra relation, SI squared equals 1. And now, well, of course, this S does satisfy that. In other words, you do get a non-trivial group homomorphism from the Braid group into GL of W, but the downside is that you forgot all the crossings. You basically, it's like, you just say it's a permutation. But that was really not like in line with the purpose of defining the Braid group, because we really wanted to know how this how to distinguish between like the crossings going on top and under, okay? Going up and like above and under. So now how can we fix this? We can try to fix this as such. Maybe I changed my notation slightly because I want to use this notation S for something else. So maybe I should say S equals P, where P of X tensor Y is Y tensor X. And what is the downside? So the downside, as I mentioned, we forgot the above under information at crossings. Okay, so basically we came down to the symmetric group, but we wanted a new theory for the Braid group, right? So what can we do? We can do the following. We can try to construct some non-trivial. Yes. Remember, S should be a map from V tensor V to V tensor V, and it should be invertible, okay? So now I can try an S which is a deformation of the previous S. So I want to deform P. So I want to deform it as such. So I take P, but I want to deform it by some family of transformations. Maybe some power series, depending on some parameter H, where the terms in this power series, this R prime, I should use R prime, not R double prime. Maybe I could just one more third. So these are R prime, R double prime, and whatever other terms. They are linear transformations on V tensor V. Okay, so this is something like a power series with coefficients being matrices, which we have done in this course before, right? When we talk about exponentials and so on. So now if I set H equal to 0, I get P back. Okay, so this should satisfy those conditions. And then this means that for H very small, if the series converges, then you get an invertible transformation. So those conditions are met. The only thing that needs to be checked is that if S still, this deformed S still satisfies this relation. Okay. And now here's a proposition. So there are many conditions that are imposed on these R and R prime and R prime. The first order condition will be on R. And the surprise is the following proposition. For if the non-trivial S above satisfies, and I want to give name. We almost ran out of time. Okay, I'll finish in a moment. So what is this relation? Maybe I call this a relation star. The star. Then R must satisfy the classical Yang-Baxter equation. So here, remember, R is some element on the endomorphism of V tensor V, but from linear algebra, we know that this is end V tensor end V. So we can think about this as some two tensor. If I call this vector space, maybe I call this E. So then I have that this R and R prime and so on, they all belong to this E tensor E's. Okay, and now, in fact, this E is also an associative algebra. So we can still like talk about this CYBE because it was defined when like this space was a Lie algebra, in particular when it's an associative algebra. And it turns out that a first order necessary condition to get a realization of Braid group by matrices, other than the one coming from like permutations, is to get a tensor satisfying the classical Yang-Baxter equation. So that's one sort of reflection of this equation connecting algebra and topology. Okay, so maybe we should stop now. So next time I want to talk a little bit more about these Lie bialgebras because, well, okay, maybe we should talk about analogs of Lie's theorem and so on, and the Manin triples. And maybe there is a little bit of time left to talk about quantum groups. So we have only one lecture left, right? So maybe, I don't know if I don't think it makes a huge difference if I just spend one lecture on quantum groups. Maybe I should just spend one lecture partly on finishing what I'm saying now, and maybe if there's extra time, a little bit about quantum groups. Is that good? Is that a plan? All right. Okay. See you on Monday.